Thank you for coming to talk. As Katie said, my name is Sara Fecadu. I am from Seattle, Washington, and I don't have a ton of hobbies besides making cookies and listening to a lot of podcasts. And by day, I'm a software developer at Nordstrom. And Nordstrom is a clothing retailer founded in 1901. And while people don't usually associate 100-year-old companies with tech, we have a thriving tech org working on innovative ways to help you get what you need and feel your best. And about a year ago, I was hired on to do a rewrite of Nordstrom.com's checkout UI. We have a nice React Redux setup, and as of last May, we've been taking 100% of customer orders. Now, why am I talking about audio streaming? Katie may have taken my joke here, but the answer is form fields. Our checkout UI has 22 form fields, and they come in different groupings for different reasons, but many of my waking moments over the past year have been spent thinking about these form fields. And I just wanted to do anything else. So I was sitting on my couch one night, reading a book on packet analysis like one does, and watching a YouTube video, and I thought to myself, how does that work? Like on the packet level, how does audio-video streaming work? So to answer the larger question, I started small with, what is audio streaming? And audio streaming is the act of sending audio files over the network. And this talk will be about on-demand audio streaming. Now, the major difference between on-demand streaming and live streaming is that with on-demand streaming, we need all of our packets to make it across the wire. Whereas with live streaming, you may be more focused on your user keeping up with the event, and a certain amount of packet loss may be acceptable. Over the past few months, I've learned that audio streaming, even when limited to on-demand audio streaming, is as wide of a subject as it is deep. And so I've picked 3 topics that exemplify what audio streaming is, why it's hard, and how to get started yourself. So today we'll talk about audio streaming protocols, TCP congestion control, and client players. Now, audio streaming protocols give us a standard for how to encode, segment, and ship your audio to the client. TCP congestion control handles congestion on the TCP layer of the network stack, and it becomes extremely relevant when we talk about on-demand audio streaming, because we're shipping larger audio files, and we need every single packet to make its way to the client in order for us to play our audio. A client player is any network-connected device with a play and pause button. So this could be your phone, your TV, your laptop, etc. And client players not only allow us to play our audio, but when paired with modern audio streaming protocols, they hold a lot of decision-making power. Now, audio streaming protocols are the heart of audio streaming. And today we'll talk about adaptive bitrate streaming and its benefits, and how to convert your own audio files to work with 2 popular audio streaming protocols. Before we get started, I want to go over some terms that will come up. A codec encodes a stream of data, and it uses specific compression techniques to get the highest data quality for the smallest data footprint. Encoding and transcoding is about taking data from one type and converting it to data of another type. Transcoding takes digital files and converts them to other digital files, while encoding can convert either analog or digital files to other digital files. Bitrate is the measure of how many bits it takes to encode a second of audio. And this number usually refers to the quality of the audio file. When I think of playing music on the internet, I think of an HTML5 audio tag with the source attribute set to the path of my audio file. And this is a perfectly reasonable way to do it. You can request and receive a single file containing an entire song, and it would be referred to as progressive streaming. And the major benefit here is you only have one file to deal with. But let's say, for instance, you have a user and they have a slow network connection and they can't download your one file. They're stuck. So adaptive bitrate streaming aims to solve this problem by encoding your audio at multiple bit rates and allowing the client player to decide which quality is best for the user to listen to your audio uninterrupted. This allows more users to access your audio, but it does add a layer of operational complexity, as now you've got a lot more moving parts. The audio streaming protocols we'll talk about today not only leverage adaptive bitrate streaming, but also use standard HTTP web servers. They do this by encoding your files, segmenting them, placing them on a web server, and then once your audio is requested, partial audio files are sent to the client one at a time. And here's the secret to our modern audio streaming protocols, is it's more of a series of downloads than it really is a stream, but we'll refer to it as streaming anyway. The two most popular audio streaming protocols today are HTTP live streaming, or HLS, and dynamic adaptive streaming over HTTP, or Mpeg-Dash. Now, HLS was created in 2009 by Apple to support audio-video streaming to mobile devices, and it is the default streaming protocol on all Mac OS and iOS devices. Mpeg-Dash, on the other hand, was created as a direct alternative to HLS, and it was created by the Dash Industry Forum, who want to make Mpeg-Dash an international standard for streaming. Now let's take a look at these protocols side by side. HLS takes your audio files that are usually of the type AAC, MP3, AC3, or EC3, encodes and fragments them into transport streams or fragmented MP4 files. Those segmented files are then represented in a playlist. If you have multiple bitrate streams, each stream will be represented in a media playlist, and all your media playlists will be represented in a master playlist. With Mpeg-Dash, it's codec agnostic, so in theory you could convert any audio file to work with Mpeg-Dash, and it will be fragmented into a fragmented MP4 file. Those fragmented MP4 files will then be displayed in a XML manifest file called a media presentation description. Okay, we've talked about what files will be used and what they'll be segmented into, but how do you get it there? You've got this audio file. What tools are available to allow you to convert the audio file? Well, you've got options, but most of these options are paid options, except for FFmpeg, which is an open source command line tool that, among lots of other things, allows you to convert your audio files to be used with HLS and Mpeg-Dash. However, I found the learning curve for FFmpeg to be pretty steep, and a lot of the documentation about creating streams for HLS and Mpeg-Dash were aimed at people creating video streams. So instead, I used Amazon Elastic Transcoder. Now, Amazon Elastic Transcoder is an AWS offering that converts files of one type to another. In our case, we're going to be taking an audio file and converting it to be used with HLS and Mpeg-Dash. And using the AWS console, it's pretty much plug and play. You tell Amazon Elastic Transcoder what type of files you have and what type of files you want, and it outputs the stream for you. And even though it's easy to use, it's not a free service. So if you were going to be converting a lot of files, it may be worth your time to learn more about an open source alternative like FFmpeg. My workflow when working with Amazon Elastic Transcoder was to upload my file to an S3 bucket, which is S3 is an AWS object store. I then told Amazon Elastic Transcoder where my audio file was and what settings I needed it to convert my audio files to. And Amazon Elastic Transcoder output my streams back into that same S3 bucket. And I downloaded them for us to explore. So this is the basic set of files you would get with an HLS stream. And it kind of looks like a lot, but we're going to break it down into 4 groups. In the top left, you'll see the master playlist. And in our case, we have 2 bitrate streams represented. And they will be linked out from the master playlist. And then in the top right, you'll see those media playlists, which have each bitrate stream. And those will contain all of our links to our transport stream files, which are the fragmented audio files, represented in both the bottom left and the bottom right. On the bottom right, we have our 64K bitrate stream segmented audio files, and in the bottom Oh, did I get that backwards? I'm not really good at right and left, but in the bottom section, you'll have your fragmented audio files. And we're going to take a closer look at those so you can see really what's in there. So this is the entirety of the HLS master playlist. It contains information about the specific bitrate streams and links out to those media playlists that represent the streams themselves. Let's take a look at the 64K bitrate stream media playlist. It has even more information about the stream, including caching information, the target duration of each segmented audio file, and most importantly, links out to our transport streams. This is what one of those fragmented audio files looks like. And there's something a little interesting going on here. If you'll notice, it's color-coded, and I kept trying to figure out why, but then I realized a transport stream has the file extension .ts. And something else has the file extension .ts, which is TypeScript. So please just ignore all the colors. It's just a binary encoded file. Now our Mpeg-Audio stream has fewer files and looks a little bit more manageable, but the structure is very similar. We have our media presentation description, which is an XML manifest file that contains all of our information about the stream. Then below, we have our 2 segmented audio files. All of the segments are encapsulated in a single file, but within them, there are segments. So that's why there are fewer files in the Mpeg-Audio stream than in the HLS audio stream. Now, taking a look at the media presentation description, you see a lot of stuff here, but there are 3 important elements. All bitrate streams are represented in a representation tag. And then all bitrate streams are enclosed in an adaption set. Within the representation tag, we do have our URL to our audio files. And taking a look at one of those audio files, we'll see it looks fairly similar to the segmented audio file we saw with HLS, minus the color coding because it's a .mp4 versus a .ts, and Visual Studio Code is not confused in this case. Now, earlier we talked about progressive streaming, which is just streaming an entire audio file all in one go. And we used an audio element and a source attribute with the path of our audio file. With Mpeg- and HLS, it's very similar, but instead of having the path to our audio file, we have the path to our manifest file, which is our master playlist for HLS, or our media presentation description for Mpeg-. And we're going to take a hard left here, and we're going to talk about the second topic in my talk, which is TCP congestion control. And TCP is a transport layer protocol, and it has mechanisms in both its sender and receiver, which are defined by the operating systems of each to react to and hopefully avoid congestion when sending packets over the wire. And these mechanisms are called TCP congestion control algorithms. And today we'll talk about packet loss congestion control and why it isn't so great. And more specifically, we'll talk about the role of the congestion window and duplicate acknowledgements in packet loss-based congestion control. Before we get started, some more terms. Bandwidth is the rate at which data can be sent, and throughput is the rate at which data can be received. The congestion window is a TCP variable that defines the amount of data that can be sent before an acknowledgement is received by the sender. Let's say you have a user who's requested your audio file from the server. Your audio packets will travel down the network stack, across the physical layer, up the data link layer and the network layer, and it arrives at the transport layer, and unfortunately, there's congestion right before we've reached our destination. Now, traffic congestion and network congestion have very similar beginnings. Either too many cars or too many packets have entered the roadway, and there's just nowhere for them to go. With traffic, you just gotta wait it out. But luckily for us, TCP congestion control algorithms allow some packets to continue flowing over the wire even during congestion. And before we get to the specifics of these TCP congestion control algorithms, let's talk about the TCP happy path. We're going to start with a single packet, and it's going to be sent from the sender to the receiver, flowing through the receiver's buffer, and then being acknowledged by the receiver and having an acknowledgement packet sent back to the sender. Now, earlier we talked about the congestion window, which is the amount of data that can be in flight before a sender receives an acknowledgement. Another way of thinking about the congestion window is as a sending rate. So as the sender receives acknowledgements, the congestion window grows. And as the receiver's buffers fill and they drop all excess packets, the sender responds by shrinking the congestion window. A second way of thinking about the congestion window is as a bucket. And as packet loss occurs, the bucket shrinks. And as acknowledgements are received by the sender, the bucket grows. There's a slight oversight in the bucket explanation in that the receiver has no way of telling the sender that it is dropping packets due to congestion. But one option the receiver does have is to send a duplicate acknowledgement. And a duplicate acknowledgement is sent if the receiver is trying to process out-of-order packets. Now the sender in this example sends packets 1, 2, and 3. For the purposes of our example, the receiver is not going to process them right away. So that when we send packet 4, the receiver's buffer is full, and packet 4 has nowhere to go. So packet 4 is dropped due to congestion. And the receiver moves on to process packets 1 and send an acknowledgement for packet 2, and for packet 3. However, when it looks at packet 5, it says, I can't process you because this would be an out-of-order packet. So it drops packet 5 and sends back its last acknowledgement, which was for packet 3. The sender sees this duplicate acknowledgement and is tipped off that it needs to send packets 4 and 5 again. So a more truthful version of the bucket metaphor would be that the congestion window shrinks as old acknowledgements are received by the sender, and the congestion window grows as new acknowledgements are received by the sender. The first TCP congestion control algorithms were written in the mid-1980s, and the most recent were created just a few years ago. And today we'll talk about 2 algorithms, TCP Reno and BBR. And TCP Reno is the classic packet loss-based congestion control algorithm. And BBR was created by a team of Google engineers just a few years ago to address issues that they saw when using packet loss-based congestion control algorithms. So TCP Reno begins with a slow start period where the congestion window is set at some rate increasing by, it's set at some value, increasing by some rate. And as the sender receives acknowledgements, the congestion window grows by 1. And as the sender has to resend packets, the congestion window is divided by some rate. I've chosen half, so it's divided by 2. And the main issue with TCP Reno is that it assumes that small amounts of packet loss are congestion. And in a world where the sender doesn't know the state of the receiver's buffer, and the receiver is unable to tell the sender that it has room left to process packets, you're left with an internet that's moving at a fraction of its capacity. So in 2016, BBR was created to help you get the most out of your internet connection. And it does this by trying to find the optimal point where sending rate is equal to bandwidth. So in theory, you should be able to send a packet from the sender to receiver and have it move on to the application without any queuing. Some companies have reported positive outcomes when using BBR in their production systems. Firstly, it only has to be implemented on the sender side and has been available in Linux operating systems using kernel 4.9 or higher. In an experiment by Spotify, they found that BBR increased bandwidth for their low bandwidth users by 10 to 15%, and increased bandwidth for their medium group by 5 to 7. Additionally, they found users in Latin America and Asia saw additional increases. But is it a fair algorithm? Fairness, or using your fair share of bandwidth, is the goal of every TCP congestion control algorithm. And in experiments by Google and Spotify, they found that BBR was able to coexist with packet loss-based congestion control algorithms like TCP Reno or Cubic. However, some researchers found that BBR's initial start algorithm pushed Cubic senders back to a point where they couldn't reestablish their fair share of bandwidth. And this is an issue that's currently being looked at both in and outside of Google. we've reached the final section in this talk. And so far we've talked about how audio files are processed to be streamed and issues that may occur as they travel to devices. We'll wrap up by talking about the role of the client player and how to create your own audio streams. Now, I'm a pretty big fan of Spotify, and I use it regularly. But have you ever looked at what's being sent back from the web server to create those audio streams? This should look pretty familiar to what we were looking at with our segmented audio files with HLS and Mpeg-. But when I first saw these, I did not have this context, and I kept thinking, do I need to write some client-side JavaScript to get this to play on the internet? Is there an NPM package out there that I can use? Or is there something really simple and obvious going on here that's going right over my head? And luckily for me, and maybe all of us who write JavaScript for the web, there is, because HLS and Mpeg- have handed over a lot of responsibility to the clients that process their streams. And this not only includes picking the correct quality of audio to play, but it also includes allowing elements like the audio element to process segmented audio files without any modification. And most browsers do this by leveraging the Media Sources Extension API and the Encrypted Media Extensions API. Additionally, libraries like hls.js and dash.js are available while cross-browser support is still low. But a small side note, if you need to support iOS Safari, you just have to use HLS. But with most other browsers, you'll have options. So it would have been really fun to reverse engineer Spotify's audio player, but I got tired of reading their minified code, so I decided to make my own audio player. And I started with a cassette that I found from a box of cassettes. And I chose it because it has the words Map Squad written on it. And I used my iPhone's voice memo application to record the audio, so the quality is so-so at best. But it works, and you can try it right now, but maybe wait till the end of the talk because I want to show you how it's made. The entire application is a single index.html file that has an audio element in its body. And when loaded into the browser, an immediately invoked function expression runs, the init function. And at the top of the init function, we define a variable called audio that's equal to our audio element. Next, we'll see if the Media Sources Extension API is supported in our browser. If it is, we'll assume we can use dash.js to enable Mpeg- in most browsers. We'll pass the path of our media presentation description to the dash.js media player. And when the audio player is initialized, our audio will be loaded with it. If the Media Sources Extension API is not available, we're going to assume we're using iOS Safari, and we need to have an HLS stream. And we'll do this by setting the source attribute of our audio element to the master playlist, or the path to our master playlist. And this file is all you need to stream audio to most browsers in 2019. If you want to try it out in the browser for yourself, or you want to create your own audio streams, please feel free to fork this repo. Thank you.